The first example we're going to be thinking about is finding the work needed to pump all of the water out of a tank. If this tank has length 3 and a side face given by this parabola y equals x squared for x between -1 and 1. We're going to use that the density of water is 1,000 kilograms per cubic meter and that gravity is 10 meters per second squared. Okay. So the principle we're going to use is that the work is the integral of a bunch of little works. Okay. And so what we're going to be thinking of doing is taking our tank of water, and we're going to be thinking of cutting it up into a bunch of these super thin slices, a slab of water, if you will. And we're going to assume that this is a slab of water at height y. Okay. With thickness dy. So it's going to be really, really thin. Okay. And what we're going to do is figure out a formula for the work to move this slab up to the top of our trough, up and out. Okay. And so dW then is going to be, this is the work to move this slab out of our trough, or tank, I guess. And so let's take a look. We're going to break this down. Okay, so we're going to use our principle. So work is force times distance. And because it's such a thin little slab of water, the force we're going to need is not going to be very big. So I'm writing dF. And then we're multiplying it by distance. So remember that caret means multiply. Okay. So if we're at height y, we want to think about how far we need to move it to get it up and out of the tank. Okay. And it helps here to have a side view of what's going on. So here's a side view. This is the parabola. Oops. Okay, y, that's all right. Y equals x squared. That's fine. And it's going from -1 to 1. X equals 1. X equals -1. And if we take a look right where this height should be, then this point is at 1, 1. Okay, so this y value is y equals 1. And so our slab is at height y. Okay. And if we want to know how much further we need to, like how much we need to move it to get it out of the tank, well, that's going to be this distance. And we can calculate the top minus the bottom. On top, we have 1. On the bottom, we have y. And so the distance we need to move this slab is 1 minus y. Let's just double check that this makes sense. If we're at the bottom of the tank, down here, our y value, our height is 0. And so we need to go all the way up by 1. Okay. So we do 1 minus 0 and we find this is the right value. If we were up at the top already, our height is 1. When we look at this distance, it's 1 minus 1 or 0. Okay, so I believe this distance. Next, we want to figure out the force that we need to move this slab. So this force, to find this out, we're going to use mass times acceleration. Okay, our because gravity's pulling down and we want it. What we're using is we want to balance gravity out, so we need to counteract gravity. So our mass here is something small, and we're multiplying it by the size of gravity. So 10 meters per second squared. Notice this is going to be positive, opposing gravity. Okay. Now our mass, we don't know what our mass is, but we do know density of water. So we can think of mass as a density times a volume, or density. I guess maybe the more usual way of writing it is that density is mass over volume, but we could always rewrite this as mass equals density times volume. Okay, and so this little mass is given by our density of 1,000 kilograms per cubic meter times our volume. Since this is a thin little slab, we assume it doesn't have like a huge amount of volume. So we're writing dV. Okay. Now, if we take a look at our slab, our volume is, we can approximate using the cross-sectional area because it's really thin. The cross-sections should be pretty similar along the top and the bottom of the slab and throughout. So we're going to take our cross-sectional area of the slice at height y times our thickness dy. Okay. And so we know everything in here except our cross-sectional area. And if we take a look at this picture, notice that we see this cross-section is going to be a rectangle. I'm just going to draw this out. Actually, like this. Okay, so our cross-section is a rectangle. In one direction, we're length 3. In the other direction is this width along this line where we have height y. Okay, and so what we're going to do is just find the change in our x values from the right to the left. So on the right-hand side, we have x equals square root of y. And on the left-hand side, we had x equals negative square root of y. And so this total length is going to be square root of y minus negative square root of y, or 2 square root of y. So our area here is going to be 6 square root of y. All right. Okay, and so we now have all of the pieces. Our work is going to be this integral. We have water from a height 0 all the way up to the top here at height 1. We're going to be multiplying our cross-sectional area, 6 square root of y, times our density, 1,000 kilograms per cubic meter. I'm going to put the dy at the very end, that thickness. We're multiplying by 10 meters per second squared, and this distance 1 minus y. All right, so the hard part is getting this set up. And now we're just going to integrate all of the constants. I'm going to multiply out in front. So we had 1,000 times 10 times 6. So this is 60,000. We're integrating from 0 to 1. Instead of writing square root of y, I'm going to write y to the 1/2. And we're multiplying it by 1 minus y dy. We can distribute this. Okay, and we get the integral of y to the 1/2 minus y to the 3/2 dy from 0 up to 1. Okay, All right, and let us integrate. So this gives us 60,000 times y to the 3/2 over 3/2, so times 2/3, minus y to the 5/2 over 5/2, so times 2/5. We're evaluating between 1 and 0. So next up, we're going to plug in y equals 1 and y equals 0 and take a look. So plugging in 1, here we get 60,000 times 2/3 minus 2/5. And then when we plug in 0 to both terms, we just get 0. Okay. So this is 60,000 times, 2/3 is 10/15, and then 2/5 is 6/15. 60,000 times 4/15. 60 divided by 15 is 4. So this is 4,000 times 4. Or 16. So 16,000 joules are required. And we can write this 16 kilojoules. Great.